Hi guys, in this video we're going to look at conformational isomerism, which is a type of stereoisomerism where molecules can adopt different shapes due to rotation around carbon-carbon single bonds. Obviously, conformational isomerism is very important when we come to look at stuff like drug molecules, because enzymes receptors are stereospecific, so will only tend to bind a molecule with a particular shape. Now, what we've got here is probably the simplest molecule that we could look at for this example, which is ethane. And ethane can adopt different shapes due to the fact you can get rotation around this carbon-carbon single bond. So what we're going to do is we're going to imagine we're looking at the molecule from this direction. And we can look at this sort of diagram here, and this carbon here, we can imagine this is a carbon, and that there is carbon 1, and carbon 2 is directly behind carbon 1 there. And we can see that these three hydrogens in blue represent these three hydrogens in blue here. Now, due to the fact that this carbon-carbon bond can rotate, these green hydrogens can adopt different arrangements in space relative to these blue hydrogens. One particular arrangement in space is where these green hydrogens are as far apart as possible from the blue hydrogens. And this has got a special name. This type of conformation, this shape, this arrangement of atoms is called a staggered conformation. So we call this then a staggered conformation. Now, if we rotate this carbon-carbon bond by 60 degrees, like this, then what we now get is these hydrogens are, or the green hydrogens are directly behind the blue hydrogens. And now this is called a an eclipsed conformation. And the eclipse conformation introduces something called torsional strain. So the fact that these two groups are near each other gives you something called torsional strain. And because of this torsional strain, the eclipsed conformation is the least stable form. Staggered conformation, the most stable form. So that's ethane. We can adopt the similar principles for looking at the different conformations in a slightly more complex molecule, and here we're going to look at butane. And now we're going to look along the bond between carbons 2 and 3. So we're going to be looking in this direction along the carbon 2-3 bond. And we can see that we've got the blue CH3, the two blue hydrogens corresponding to the blue CH3 and the two blue hydrogens. So this is carbon 2, and directly behind that is carbon 3. And we're looking at the different spatial arrangements due to the rotation of this bond between carbons 2 and 3. So let's have a look at the first possible conformation. This is where the CH3 groups are in a, or we've got a staggered conformation where the CH3 groups here are as far apart as possible. And we call this then a anti-periplanar conformation. So this conformation is called anti-periplanar. Now, if we rotate this bond between carbons 2 and 3, if you rotate this 60 degrees, then we would get the following conformation. We now get an eclipsed conformation. So remember, we're going to rotate this up here by 60 degrees, which will now mean the CH3 group is here, a hydrogen there, and we have a hydrogen there. And this eclipsed conformation is called an anticlinal conformation. And again, we've got some torsional strain there. What we can do is we can rotate this another 60 degrees, and that would give us the following conformation. We get another staggered conformation, but it's a different staggered conformation to what we looked at a little bit earlier on. Why? Because now these two CH3s are next to each other rather than being far apart. And this here is something called a steric strain. And we sometimes call this thing here we call this a gauche interaction. And this arrangement in space is called a synclinal. With our gauche interaction. What we can do is we can rotate this another 60 degrees. And that would give us the following conformation. It's going to be another eclipsed one, where the CH3 groups are now behind, or the green CH3 group is behind the blue one. And this here will introduce steric and torsional strain. So we've got torsional strain and steric strain. And this here is called a syn periplanar conformation. So if we have a look at these different conformations, the most stable would be the antiperiplanar, because there's no steric or torsional strain. These bulky groups are as far apart as possible. The next most stable is going to be the synclinal. Again, both the eclipsed conformation, both staggered conformations are always going to be more stable. Staggered conformation will always be more stable than eclipsed. So this would be number 1. This would be number 2. The next most stable would be the anticlinal. The least stable is the symperiplanar, because it's got both torsional and steric strain. So they're the different arrangements in space for example, a molecule like butane. But let's now have a look at a biomolecule. We're going to have a look at acetylcholine, which is this molecule here. And we're going to have a look along the bond between carbon 4 and 5. And we're going to look at the effects of the rotation around this bond. So acetylcholine is a very, very flexible molecule. Lots and lots of different single bonds that can rotate. And that can lead to acetylcholine adopting lots and lots of different shapes. Now, this is really important, because the fact it can adopt lots of different shapes means that it can bind to pretty much all the cholinergic receptors in the body. Okay, it can switch on all the receptors because it can adopt so many different shapes. So we've got to imagine these different receptors will all have kind of different shapes. But because acetylcholine can change its shape so much, acetylcholine can switch on all these receptors. Okay, so if we have a look, for example, at the different conformations of acetylcholine. Now, what we could have then is we can have the molecules being in the antiperiplanar arrangement. And the antiperiplanar arrangements, remember, is where the bulky groups are as far apart as possible. So in this case, as you can see there, this is carbon 5, where I've got my NMe3 and my 2 blue hydrogens. That's attached to carbon 5. And obviously directly behind that is carbon 4, and I've got my 2 hydrogens in green, which correspond to these 2 hydrogens here. And then all this group here, I'm calling an OAC, where AC stands for acetyl. So this here would be the most stable antiperiplanar arrangement, where the bulky groups are as far apart as possible. There's no steric strain in this staggered conformation. Now you may assume that obviously because it's the most stable that it's always going to bind in this conformation, but not necessarily, because if that was the case, then acetylcholine would only bind to certain receptors. It's flexible and can change shape. So for example, it is possible for this, for example, to adopt this other staggered conformation, this synclinal conformation, where we do have this gauche interaction here. So we've got this, remember, we've got a gauche interaction there with the two bulky groups near each other. But there is not a massive energy difference between these two. So acetylcholine could potentially bind to certain receptors when it's in the gauche conformation, because the energy that it gains by binding to the interaction, this stabilisation energy gained from binding to the receptor, can compensate for this slightly less stable conformation. Because remember that when these groups bind to receptors, it releases energy, because it sort of bonds are formed in, even if they are really weak intermolecular forces. Now, what we potentially in terms of drug design, what we want to do is we want to design molecules which will switch on certain receptors and not others. Which is why we couldn't give, for example, acetylcholine as a drug, because it would have so many side effects, because it would bind to many, many different receptors. When we're designing drugs, we want drugs to bind to one specific receptor. So that may mean that we want the spatial arrangement of certain atoms to be fixed in space. And an example of this would be a molecule here called muscarine. So this here is called muscarine. And we can see that it's got similar structure to acetylcholine. Now you can see that acetylcholine has got an NCCOCC, same as muscarine, NCCOCC. So muscarine has got the same sort of acetylcholine skeleton, but it's been locked into a specific conformation. These atoms are arranged in a certain way in space and they cannot move around, which will mean that it will only bind to certain receptors and not others. And that's kind of a really good thing when we're looking at drug design. We want drugs to bind to certain receptors. So if we can get some understanding of the spatial arrangement the atoms must be in, that'll give us a way to design drugs which are specific for certain receptors. So that gives you a quick overview of conformational isomerism, and also hopefully you can see why understanding spatial arrangements of atoms is important.